Okay, Landon, this is for you since you're not here. Hope you're having a good day wherever you are. We're going to review now for, let me get the old camera set up here. Camera adds 50 pounds. That's what they say. Oh my goodness. Well, test tomorrow, very similar to this. And I was working with Anna a little bit last night after school. And one of the things I think is really important is take some prior knowledge that we need. Now, prior knowledge, when I say something like that, I mean, if we're dealing with solutions and we need to get number of moles of one of the components, so you have to remember that the molarity of the solution, which is usually given to you, times the volume in liters is equal to the number of moles. That's one way to get number of moles. And of course, the other way to get number of moles is to go, is to take your mass, and then, like say I've got 50 grams, and then then you go 1 mole, and you put the molar mass down there, molecular weight. So that would give you your number of moles as well. Don't forget that. Also, when I was thinking about this, a lot of times the question will say, hey, calculate the heat of something and then tell me heat per mole in like a chemical reaction. And so for example, if a question says to you, give the enthalpy of the reaction, they're going to want to know based upon a certain number of, based upon the number of moles you have. So you take Q, divide it by your number of moles, and that would give you your delta H for the reaction, or your enthalpy. Okay, so those are some things to really keep in mind. Volume in liters, molarity, number of moles. Mass divided by molar mass, number of moles. Heat divided by number of moles would give you your enthalpy for reaction. Sometimes a question might say, how about heat per gram? Well, if you have a Q divided by the number of grams, that's going to be your heat per gram. Think of per as meaning divided by. Okay? All right, so let's get started. Oh, wow. Wait, hang on. This is one of those fancy erasers that I can just rip that part off, get rid of it. It doesn't do that much better. All right, so let's take a look here. Oh, questions 1 and 2. Those are like gifts from God. Because we know delta E, the change in overall energy of a thermodynamic system, is equal to heat plus work. Heat and work. You might say, well, what do you mean by work? If I have a chemical system, let's say, for example, I have a gas that's expanding and changing the volume of a container, like we learned in the gas laws, that would be an example of a system doing work. So if the system is doing work, W is going to have a negative sign on it. If the surroundings are doing work on the system, the value will have a positive. If heat is leaving the system, uh, and causing a change, an increase in temperature of the surroundings, then Q is negative for the system. If the system is absorbing heat, Q is going to be positive. So let's take a look here. We have delta E. If Q is negative 47, and that's kilojoules, and work is positive 88 kilojoules. Who's got it? What do you got? Was that 30? 40? What? 41? Positive. And what's the unit? Kilojoules. How'd you like to have a test of just all these?
Yeah.
Yes.
Okay, now this is one. Calculate W, calculate the work. If, see, so we got delta E is Q plus W. And so delta E minus Q is going to be equal to W. So our delta E is 129 kilojoules positive. And we're going to subtract from that the work, which is 82, or the heat rather, 82 kilojoules. So what'd you get for that?
47.
47 kilojoules of, that's going to be the work. So far, the system hasn't done any work on the surroundings. Delta E, this is a real easy one. If Q is equal to positive 47 kilojoules and work is equal to 0, then the change in energy is just equal to 47 kilojoules. And in none of these cases is the system doing work on the surroundings, because they always have a positive value. Okay, this one you got to think a little bit about the signs on number 2. The system absorbs 72 joules, so that's going to be of heat. That's going to be positive 72, while 35 joules of work is done on it. Well, the work is also going to be positive, and it's 35. So we've got 107 kilojoules would be the total heat, or total energy change for that. And it's going to be positive. Okay, the system absorbs 35 joules of heat while performing 72 joules of work. So the sign on heat's going to be what? Positive, right? Absorbing heat. System is absorbing heat, so that's positive. It's an endothermic process. While performing 72 joules of work. So if the system is performing work, what's the sign? System's doing work. Negative. Just think of it this way. If the system is giving off heat, it's negative. If it's doing work, the work is negative. It's doing something to the surroundings. So it's, losing that energy to the surroundings. Okay. So what is that for part B? What do you get for that number? You guys are awake this morning. Morning, Mr. Phillips.
Hi, I'm Mr. Gargis. I took the kids down there. I just came up with an idea.
Hang on, let me pause this. Absorbs 35, so it's going to be positive 35 joules. Well, this was just joules up here, while performing 72 joules of work. So 35 minus 72 is what? What's that? 37? Negative 37 joules. So to get the total delta E for the entire process, you're going to just add these 2 delta E's, and that's it. Okay, let's move along. Are the following processes exothermic or endothermic? Remember, exothermic means you give off heat. Endothermic means you need to absorb heat. So if we are looking at HCl poured into water and the water gets hotter, little rhyme there. Is that exo or endo? The surroundings are getting hotter. The temperature is increasing. Exothermic, yes, yes indeed. How about the evaporation of water? Do we have to put in heat to get water to evaporate? Yeah, it's an endothermic process. If the surroundings are gaining heat, you always have those two things. I mean, the water's the system. We want to get it to evaporate. It's going to evaporate a lot more quickly if I, let's say, if I drop it on a hot say a hot pan than if I drop it on the counter. So these things are very, very intuitive, hopefully. How about the conversion of frost to water vapor? Think frost on your windshield, and I want to change it into water vapor. Do I need? It's endothermic. You have to put energy in order to get the frost to turn to water vapor. Did you guys have a hard night or something last night?
Yeah.
Everyone's just like, ugh. That's okay. How about the combustion of methane? Combustion of methane. Burning. This is exothermic. Yeah. Okay. In a calorimeter, silver nitrate and HCl are allowed to react. Okay. Let's take a look. I don't like this question. I don't remember where I got it. I always used to steal them from old books. But we'll write it out anyway. AgNO3 plus HCl, and that's going to give HNO3 plus AgCl, which should be a solid, but the question goes on, and we'll just go with the info in the question. They say you get a solution of silver chloride in this question, but really you would get a precipitate, but that doesn't matter. Let's just work through the problem so you can see the mechanics on it. And they show you the net ionic equation. Silver ions plus chloride ions to give silver chloride. And notice everything is in a 1-to-1 molar ratio. So in this case, it says one of the products formed, and that's all we know about is the products, is 50 milliliters of a 0.10 molar AgCl solution, which really you wouldn't get a silver chloride solution, but let's just go with it, pretend we do. And it says the two solutions were initially at 22.6 degrees C, and the final temperature is 23.4 degrees C. Calculate the heat that accompanies this reaction in kilojoules per mole of silver chloride formed. So all we know is that we have 50 milliliters formed of this. So we can make the assumption that maybe we took 25 mils of each solution and dumped them together. So Q is equal to mc delta T. What's my mass going to be? Well, I can see how you may have thought that, but the only information we have
Does it say on the back?
Oh.
The combined solution is a total mass of 100 grams.
Oh, okay. Yeah, I didn't even look at the back of that. All right. I should really go back and look at these old exams. So, all right. So we have 100 grams. And what do we then know about the specific heat capacity? What are we going to use? Good. 4.18 joules per gram per degree C. And then we have our delta T, which is back on the front here. 23.4 minus 22.6. What, 0.8, right? So let's just multiply these all together and we'll get our heat. And I get 334.4 joules. Okay, 334.4 joules. Now that's the heat that was absorbed by the water, the surrounding. So for the reaction, we have to change the sign. So Q for the reaction for the system is going to be negative 334.4 joules. Now, they go on to ask in this question, or I guess I went on to ask in this question, calculate the heat that accompanies the reaction in kilojoules per mole of silver chloride formed. So, I've got the joules. I know that I've got 50 mLs of 0.1 molar solution. So, how many moles do I have? You gotta change. I can see why you said 5 because you multiply. Remember, we have to change that to liters. If you have milliliters, guys, change them to liters. So that's going to be 10 100,000 times 0.1 0.005 mole of AgCl. So now what we're going to do in order to get the delta H per mole of silver chloride, it's going to be negative 334.4 joules divided by 0.005 moles. And you're going to get a pretty big number. I come up with, I'm doing this, let's see if Len can see this number over here. I get a big number, which you should. I get 66,900 joules per mole or 66.9 kilojoules per mole. You guys getting them so far? You getting the answers right? Good. All right. We did 5 and 6 yesterday. Those were the Hess's Law problems. I don't think we need to go through those again, do we? Yeah, you guys, once again, it's just a matter of manipulating equations and adding up the delta H's. So since we went over those yesterday, we'll go ahead and look at some of the others. All right. Now this is a good one. This is a bomb calorimeter question. It says, and they're asking you to compare two different heats of combustion. It says hydrogen gas obtained by decomposing water is a potential substitute for natural gas. To compare energies of the two, an experiment was carried out in a bomb calorimeter with a heat capacity of 11.3 kilojoules per degree C. When a 1.5 gram sample of methane gas was burned in the calorimeter, the temperature increased by 7.3 degrees C. When a 1.15 gram sample of hydrogen gas was burned, the temperature increase was 14.3 degrees C. Calculate the energy of combustion per gram for hydrogen and methane. All right, well, let's do the methane first. Bomb calorimeter, Q is equal to C delta T. No mass in there because the mass is already part of the calibration for the heat capacity of the bomb. So, let's take a look here at the methane. So we've got 11.3, and that's going to be joules per degree C, and our delta T was 7.3 degrees C. So let's figure out that heat, and this is for the methane, 11.3 times 7.3, and that's 82.49 joules. Kilojoules, yeah, kilojoules. Very good, thanks. And now if we want kilojoules per gram, we just divide by the number of grams, which is 1.5. So a heat per gram, I'm going to take 82.49 kilojoules, divide it by 1.5 grams, and that'll give me kilojoules per gram. And you get 55 kilojoules per gram of methane. Pretty easy. And now let's do the same thing for the hydrogen gas. And the bomb calorimeter is the same, has the same heat capacity. And our delta T, though, is different. It's 14.3 degrees C. Degrees C cancel, kilojoules are left, and we've got Q is I should have in the last thing changed the sign to negative because we are burning these things that are giving off heat. So forgive me if I didn't do that. 11.3 times 14.3, and that's 161.6 kilojoules. So that would be a negative value actually, since we're combusting this. System's giving off heat. And now Q per gram, heat per gram, negative 161.6 kilojoules divided by 1.15 grams. And that's going to be negative 140.5 kilojoules per gram of H2. So hydrogen gas is actually sort of a more efficient fuel in terms of producing heat energy. Okay. Any questions so far? They're good.
Why did you have to choose for that?
Because we have two different things we're comparing.
Okay.
We're comparing the heat of combustion of methane with the heat of combustion of hydrogen. So you do it twice, and you say which one gives you more heat. Okay. All right. Now we are on the types of problems where we have to go to the back of the book. So let me get a book here. which I am using as a pedestal for my laptop. Thank you so much. All right, so tomorrow we'll probably, instead of me printing off these tables, because we have a shortage of printer paper apparently, we'll just go ahead and use the appendices in our book. So starting on page A21, we have all of our delta H values for these heats of formation. And don't forget, some of them are pretty easy because all we have to do is, if it's an element in its standard state, then we look and it's going to be 0. So we can right away just go ahead and do that. All right, so eraser. I would lose my head if it was not attached. Okay. The delta H for a reaction is equal to the sum, the delta H's for the products, minus the sum of the delta H's for the reactants, each thing multiplied by its stoichiometric coefficient. So we'll go through, we'll do these, just for kicks. Was this the last problem on the sheet, this number 8? Yeah. So I have to look up the products. So for A, I need to get a sodium chloride solid. So sodium chloride, I'm going to go to the page that has sodium, which is page A23, and sodium chloride solid is negative 411 kilojoules per mole. Times 1 mole. So it's all 1 to 1. And H2O gas. So we're going to go to H2O gas here.
Wait, Dr. Potts, where did you find that one?
Page A23. Go to where it says sodium, down at the bottom. First column.
All right, no.
Do you see it or no? Here, I'll show you.
Because this one is NaO, it's negative 27.
No, we're doing the products first.
Oh,
Products
sorry.
minus reactants.
Okay.
Yeah. We're going to need that number, though. Okay. Look at the products first. If you get it the other way around, then you're going to get the opposite sign on your delta H. Now we're going to look for HCl, hydrogen chloride gas. Or, I'm sorry, water gas. You got me looking at the reactants now. Okay. All right. Under hydrogen, on page A22, first column, H2O gas is negative 242 kilojoules per mole, multiplied by 1 mole, because it's all 1 to 1. What did I say it was? 211? 242? Okay, now from that, now we're going to do the reactants. So we need that NaOH again, and that's going to be negative 427 kilojoules. And then we're going to look for HCl gas. HCl gas. We'll have to look for barium, beryllium, bromine, carbon, chlorine. Right there on page A22, first column, negative 92. Negative 92 kilojoules. And you might be wondering, why do I not write them as kilojoules per mole? Remember, we're multiplying by the stoichiometric coefficient, which just happens to be 1 mole. So the unit would cancel. All right, so let's come up with an answer for this. We got negative 411 minus 242. And this negative sign will distribute. So then we're going to add 427 and 92. And I get, for this reaction, negative 134 kilojoules per mole. That's the delta H of the reaction. Anyone get that? Good, good. Yeah, like I said, this stuff isn't difficult. It's just a matter, like I said, of keeping track of, don't get confused between your reactants and products. Look what's in the parentheses, etc. All right. So, CO2. or 2CO plus O2 to give 2CO2. All right. Well, I'll write the reaction up here because we're going to have to be multiplying by a coefficient. Okay, that's going to be 0, so we don't have to worry about that. You okay? Jeez. So I'm going to go ahead and I'm going to look up carbon compounds on page A21. And so I'm looking for CO2 gas. That's negative 393.5. So 2 times negative 393.5. And I'm going to subtract from that 2 moles times the heat of formation for carbon monoxide. And that's negative 110 kilojoules. And I'm going to go ahead and do that and see what we come up with here. 2 times negative 393.5. So I get negative 567 kilojoules for that reaction as written. Get that one, Cade? Good. Carolyn, you getting them? Good, everyone? All right, excellent. Last one then. This is the combustion of methane. CH4 plus 2O2. We don't have to worry about that. It's going to be 0 because it's an element in its standard state. This is a gas. And then I've got CO2 gas plus 2H2O liquid. Okay, so our products first, and the stoichiometric coefficients are 1 and 2 there. So the first one is going to be 1 times the heat of formation of carbon dioxide, which we just looked at earlier, negative 393.5 kilojoules. And we're going to add to that 2 times the heat of formation of water, liquid, water, negative 286 kilojoules per mole times 2 moles. And we're going to subtract from that the heat of formation of methane. So methane, CH4, negative 75 kilojoules, but we have only one of them. So negative 5. What did I say it was? Negative 75 kilojoules. Or 1 times negative 75 kilojoules. Being a little sloppy here, I guess. Negative 393.5 plus 2 times negative 286. And we're going to add to that. And I get negative 891 kilojoules for the delta H for that reaction. Okay, Landon, that was all for you. See you tomorrow.